Good evening, everyone. I am Shivani Dhok and I welcome you all for today's tutorial session, which is completely based on the content of week 5. And in week 5, the content that was covered was Z transform. So, in this tutorial, we'll basically look at some basic concepts of Z transform, like we'll revise those concepts, and then followed by that, we'll solve some good number of questions so that we can get more hold on those concepts. Like we'll try to find Z transforms as well as inverse Z transform, and some questions based on the properties of systems which can be analyzed using or with the help of Z transform. So to begin with, let us first look at some basic concepts. That is, let us start by understanding the definition of the Z transform. So the Z transform is basically for a discrete time signal x of n. So let us begin again. So we'll start with first defining the Z transform. This Z transform is defined for a discrete time signal x of n, and it has, let's say, a Z transform x of z along with a region of conversion ROC. So this is a region in which this x of z converges, and this x of z is basically defined as a summation for n running from minus infinity to infinity x of n z power minus n. So this is the definition of Z transform. Along with that, there are several properties of Z transform which are quite similar to that of Laplace transform. So the first property that we have is linearity property. That is, let's say if x1 of n has Z transform x1 of z and region of convergence R1, and x2 of n has Z transform x2 of z with region of convergence R2, then a x1 of n plus b x2 of n will have a Z transform a times x1 of z plus b times x2 of z, and the region of convergence is basically intersection of these two regions of convergence. Another thing that was discussed was this time shift property. That is, if x of n has a Z transform of x of z, then if I shift this x of n by a factor n naught, that is x of n minus n naught, then this will have a Z transform as z power minus n naught x of z. The region of convergence remains same, but there might be a possibility of addition of a 0 or a pole because of this additional factor that is coming here. So based on the sign of this n naught, we'll have either additional 0 or a pole. The next one is time reversal property. So it says that if I reverse a signal, that is I flip a signal along time axis, then this will have the Z transform as x power Z inverse, and here this Z inverse will be the ROC, such that Z inverse will belong to your ROC R1, where this R1 was, or let's say R, where this ROC R was the region of convergence of my original signal x of n. Z inverse should belong to R. Next property is multiplication by n. So it says that if I have something like this, that is n into x of n will have the Z transform as z ddz of x of z. Next property is accumulation property. So if I accumulate signals from, let's say, L equal to minus infinity to n x of L, then this has Z transform as x of Z divided by 1 minus Z inverse. So here also my region of convergence remains same, but here we may get a pole at Z equal to 1. And the last property is convolution in time. So if I have convolution of two signals, that is x1 of n convolved with x2 of n, then its Z transform is simply x1 of Z multiplied by x2 of Z, and the region of convergence is the intersection of these two regions. And these were the properties that were discussed in the lectures. And next thing that was discussed was poles and zeros. So we know that this Z transform is generally of the form, so this Z transform of any signal, or let's say any system h of Z, is of the form numerator polynomial nz upon denominator polynomial. Then roots of numerator polynomial, roots of this are zeros, and roots of denominator polynomial are known as poles. Zeros can be a part of ROC, but poles are not in ROC. And next, inverse Z transform was discussed. In this, partial fractions method was discussed and power series method was discussed. So we'll look at examples of both of these methods while solving the questions. Next thing that was discussed was the Z transform of systems for LTI systems. So we know that if I have an LTI system with impulse response h of n, and my output is y of n for an input x of n, then this y of n is simply the convolution of x of n and h of n. And if we look at the time convolution property, then y of z is equal to x of z into h of z, which implies that h of z is equal to y of z divided by x of z, and this h of z by y of z, this h of z, that is y of z by x of z, this is known as transfer function. This is known as transfer function of any LTI system with impulse response h of n. And the properties of region of convergence for causal and stable systems were discussed. So for causality, it was seen that h of n is equal to 0 for all n which are less than or equal which are less than 0, which means that this h of n is right hand sided. And for right hand sided signal, the region of convergence takes the form as mod of z max, or sorry, mod of z, that is absolute value of z, is greater than R max, where this R max is the highest magnitude of pole that we can get. And for stability, unit circle is included in region of convergence. So these two are the conditions that are for the stability and causality of the system. So these were the concepts that were discussed in week 5, and now let us look at some questions. But before that, if you have any doubt in the concepts, please let me know. If there are no questions, so let us start looking at the questions that we are going to solve today. So the first question that we are going to look is, we need to find the Z transform of this signal, that is x of n is equal to 3 into 1 by 2 power n un minus 4 into 1 by 3 power n u of minus n minus 1. So let us say that we will find the z transform of this signal using linearity property. So for that, let us say that this part of the signal is x1 of n, and this part of the signal including minus sign is x2 of n. So what I am considering is x of n is equal to x1 of n plus x2 of n, where x1 of n is equal to 3 into 1 by 2 power n into u of n, and x2 of n is equal to minus 4 into 1 by 3 power n into u of minus n minus 1. And let's say this x1 of n has z transform x1 of z, and this x2 of n has z transform x2 of z. So let us first find out what is x1 of z. So for that, x1 of z is equal to summation n running from minus infinity to infinity x1 of n z power minus n. This is equal to summation n running from, since this is multiplied by u of n, so I can start this from 0 to infinity 3 into 1 by 2 power n. We have used the definition of u of n by changing the limits from 0 to infinity, so we can just drop it, multiplied by z power minus n. So this we can write as summation n running from minus infinity to infinity, 3 will remain as it is, 1 by 2 into z inverse whole power n. This is equal to summation 3 into summation n running from 0 to infinity 1 by 2 into z inverse whole power n. So using the formula of infinite geometric progression, we can find what is the value of this. There is some question in the chat, let me check. Yeah, we can use the properties for solving finding the z transform of x1 of n, but this is the very first question and some basic questions, so I'll not use the properties right now. Once we have solved it for one example, then we'll generalize the things and use the generalized forms for solving next questions. But yeah, thank you. So this summation that we are having is actually an infinite geometric progression of this form, that is n equal to let's say n equal to k to infinity a power n, and this will be equal to a power k upon 1 minus a if my magnitude of a is less than 1, otherwise it will tend to infinity. So if I use this definition, then this is equal to 3 into 1 upon 1 by 1 minus 1 by 2 z inverse, only when magnitude of 1 by 2 z inverse is less than 1, that is equal to z, or let's say magnitude of z is greater than 1 by 2. So this I can simplify as 3 into z upon z minus 1 by 2 with mod z greater than 1 by 2. Let us now try to find the z transform of x2 of n. So x2 of z is equal to summation n running from minus infinity to infinity x2 of n z power minus n. This is equal to summation n running.
Madam, just one question. That infinite GP formula, can you just verify once again? Sigma of n is equal to 0 to infinity a to the power of n, right?
No, k.
K.
K. if k is equal to 0, then this a power k will become a power 0, which is equal to 1.
Okay, okay, ma'am.
Yeah. N equal to minus infinity to infinity minus 4 into 1 by 3 power n u of minus n minus 1. Now since this is actually flipped version of unit step and shifted, so this is non-zero only when my n is less than or equal to minus 1. So that's why I can just change the limits something like this. I'll take this minus 4 outside and change the limits from minus infinity to minus 1, 1 by 3 power n, and here there is z power minus 1 into z power minus n. Now I'll change the variable. I'll put m equal to minus n. So if I do that, then this will become summation m running from 1 to infinity with a minus 4 outside, 1 by 3 power m or minus m into z power m, which I can write as minus 4 into summation m equal to 1 to infinity 1 by 3 inverse. So I can write it, let's say it is 1 by 3 inverse into z whole power minus m. Now if I use this formula, here my k is equal to 1. So using this formula, I can write it as 1 minus 4 into 1 by 3 inverse z, or let's say this is 1 by 3 inverse is simply 3z upon 1 minus 3z, but here my magnitude of 3z should be greater than, should be less than 1, which implies that my magnitude of z should be less than 1 by 3. Similarly, I can change the sign and write as 4 into z upon z minus 1 by 3, and the region of convergence is mod of z less than 1 by 3. So what do I have? x1 of z is equal to 3 into z upon z minus 1 by 2, and here region of convergence is mod of z greater than 1 by 2, and x2 of z we have obtained as 4 into z upon z minus 1 by 3, magnitude of z less than 1 by 3. So this is what we have obtained. Now let us first try to analyze what is intersection of these two. So for that, let's say I have this real part of z, imaginary part of z, and this is the circle of radius 1 by 3, and this is the circle of radius 1 by 2, and the region that is corresponding to the x1 of z is everything that is having radius greater than half, which is something like this, and the region corresponding to magnitude of z less than 1 by 3 is this region. Now if I consider, let's say this region is R1 and this region is R2, so from this diagram we can easily see that intersection of R1 and R2 is a null set, that it is phi, it is a null set, it is empty set, and hence it means that the Z transform does not exist. Any questions, any doubts in this question? Okay, before solving the next part, let us try to generalize certain things. If we look at x1 of n, it is some constant multiplied by some this exponential factor. So let us try to generalize this part. That is, let us say that I have x of n of the form a power n u of n. Then if that is the case, and if we look at the z transform of this, that is, we are having this 3 constant as it is, and remaining part is z upon z minus 1 by 2, and here my a was 1 by 2. So the z transform of this will be z upon z minus a, and magnitude of z will be greater than 1 by 2, or specifically magnitude of a. So by generalizing, we can simply write it that magnitude z transform of this will be simply z upon z minus a, with region of convergence magnitude of z greater than a. And if I have x of n as minus of a power n u of minus n minus 1, so this also we have seen. So this x2 of n was of the form that we have some constant a minus 1 by 3 power n u of minus n minus 1, and if we observe again here, this constant remains as it is, and the z transform is z upon z minus a, and region of convergence is magnitude of z less than 1 by 3, that is magnitude of a. So let me put a magnitude sign here. Yeah. So z transform of this will be again same function, z upon z minus a, but here magnitude of z, region of convergence, will be exactly opposite. So these are two general cases which we can use every time. These are very useful while finding the z transform. Now, uh, if there are no further questions, let us look at the next part of the question. That is, if my x of n, so here my x of n is again of the similar form. So let's say my x of n is x1 of n plus x2 of n. So here x1 of n is equal to minus 3 into 1 by 2 power n into u of minus n minus 1, and x2 of n there is some question. So answer would be same and ROC would change to negative. What do you mean by ROC will change to negative? Actually, your region of convergence is always defined based on this magnitude of z, and this magnitude of z can never be a negative quantity. It is absolute value of a complex or a real number, basically a complex number. Your z is r e power j omega, and this r is magnitude of a complex number, and this is always positive. This is always positive. So this is basically defined with respect to radius of circles in the z plane. So this magnitude of z, this is my magnitude of z. So if I say that my magnitude of z is less than some quantity, let's say 1, then it will be entirely inside interior to the circle, and if I say it is greater than some quantity, then it will be outside the circle. So the quantity with which I am comparing, if I am comparing radius of a circle with a negative quantity, it does not make any sense. I will always compare it with magnitude of something, with always with a positive quantity. I hope it clears your doubt. Okay, thank you. So let's get back to this question. So x1 of n is of the form minus 3 into 1 by 2 power n u of minus n minus 1. So again, this I can simply write as 3 into minus of 1 by 2 power n u of minus n minus 1, and this is of the form 4 into 1 by 3 power n u of n. Now we have seen here it is both of the signals are having this general form. So the first signal is of this form a power n un. Second, the first signal is of the form minus of a power n u of minus n minus 1, where my value of a is 1 by 2. So if I do that, then my x1 of z, which is z transform of this, so my x1 of z will be minus 3 or 3 multiplied by z transform of this part, which is z upon z minus a, where a is 1 by 2, 1 by 2, and region of convergence is magnitude of z less than magnitude of a, that is magnitude of z is less than 1 by 2. Similarly, let's say this has z transform of x2 of z, and this is of the form a power n un, and here the z transform is z upon z minus a, magnitude of z greater than magnitude of a. So if I consider that, then x2 of z, which is z transform of this signal, will be 4 multiplied by z upon z minus 1 by 3, and region of convergence is magnitude of z greater than 1 by 3. So let us draw this intersection part of these two ROCs. So the first circle is of radius 1 by 2. So this is of radius 1 by 2, and next one is of the radius 1 by 3. So the first region is magnitude of z less than 1 by 2, that is interior to the outermost circle, something like this. And the second part, this one, is the one where my magnitude of z is greater than 1 by 3, that is this part. So this part, which is of the form of a ring, is basically your region of convergence. So this shaded part, which is intersection, or which is the overlap of both of these two, is my region of convergence. So this is my ROC, which is my magnitude of z is lying between 1 by 2 and 1 by 3, and therefore my x of z is addition of x1 of z plus x2 of z. So this I can write as 3z upon z minus 1 by 2 plus 4z upon z minus 1 by 3, and region of convergence as 1 by 3 less than magnitude of z less than 1 by 2. Any questions at this point?
Madam, in some textbooks, they express properties as in terms of z to the power of minus 1. Which is better actually, because we have to remember these properties, right, by heart?
Whichever is convenient to you, sir.
Okay, so, okay. Yeah, yeah, okay. Okay, madam.
Yeah. Okay. So the next question that we are going to look at is, we'll try to find the Z transform of this signal, where this x of n is equal to sine of omega naught n un. In the lecture, in the week lectures, the Z transform of cos omega naught n u of n was found. So let us try to find out this part. So for doing this, we'll represent sine in the exponential notation, that is Euler's notation. So we can do it in this form, that is e power j omega naught n minus e power minus j omega naught n upon 2j multiplied by u of n, and we'll try to use this for representation to find the z transform. So x of z is equal to summation n running from minus infinity to infinity x of n un x of n z power minus n. Since we are having a unit step function here, we can change the limits from 0 to infinity. So n equal to 0 to infinity e power j omega naught n minus e power minus j omega naught n whole divided by 2j multiplied by z power minus n. So this I can write as 1 by 2j summation n running from 0 to infinity e power j omega naught into z power minus 1 whole power n minus 1 by 2j summation n running from 0 to infinity e power minus j omega naught to z power minus 1 power n. So the first term here, first term is an infinite geometric progression, and therefore we can write it as 1 upon 1 minus e power j omega naught z inverse, and this will converge when magnitude of e power j omega naught z inverse is less than 1, that is magnitude of z is greater than magnitude of e power j omega naught, which is equal to 1. Similarly, this second term here, this term will give me minus of 1 by 2j 1 upon 1 minus e power minus j omega naught z inverse, and again this will converge when magnitude of e power minus j omega naught z inverse is less than 1, that is magnitude of z is greater than magnitude of e power minus j omega naught, that is magnitude of e power minus j omega naught, which is equal to 1. So both of these summations converge when magnitude of z is greater than 1. So I can simply collectively write, or let's leave it as it is. So I can collectively write that the region of convergence for this entire x of z will be simply magnitude of z greater than 1. So let us try to simplify this. So for that, I'll just take out this 2j common, and this I can write as 1 minus e power minus j omega naught into z inverse plus, we have a minus sign here, so it will be minus 1 plus e power j omega naught z inverse upon, these two will get multiplied with each other, so it is simply 1 minus z inverse into e power j omega naught plus e power minus j omega naught plus z power minus 2. So this 1 and this 1 gets cancelled, and this is simply z inverse, in the bracket I have e power j omega naught minus e power minus j omega naught whole divided by 2j upon 1 minus 2z inverse e power j omega naught plus e power minus j omega naught divided by 2 plus z in to the power minus 2. So here I have just multiplied and divide by 2 in the second term. So this factor here in the numerator is simply sine of omega naught, and this factor here is simply cos of omega naught. So this x of z I can write as z inverse sine of omega naught whole divided by 1 minus 2z inverse cos omega naught plus z power minus 2, and the region of convergence ROC is magnitude of z greater than 1. Any questions at this point? Okay. Now let us look at the next question, and here my signal is x of n a power n sine omega naught n un. Now this z transform of this part we have seen earlier. We have seen it here. So can we do something so that we can make use of that factor or that term which we had derived earlier? So suppose I have a signal x1 of n, and I know its z transform is x1 of z with a region of convergence, let's say region of convergence R1. And now suppose I have another signal x of n which is having its z transform as a power n x1 of n. And now we need to find the z transform of this, which is x of z. So let us try to find this. So my x of z will be equal to summation n running from minus infinity to infinity a power n x1 of n z to the power minus n. This I can write as summation n running from minus infinity to infinity x1 of n into a inverse z whole power minus n. I have just taken this a power n along with this z in z power minus n and brought this sum. So if I compare this with the z transform definition of x1 of z, this is simply x1 of a inverse z, and now my ROC will be such that magnitude of a inverse z will belong to R1. Now we'll try to make use of this property which we have just derived. So now here my x of n is given as a power n sine of omega naught n into un, and this part is x1 of n, this part is x1 of n, and the z transform of this we had found in the previous question, which is obtained something like this. So its z transform is simply z inverse sine of omega naught whole divided by 1 minus 2z inverse cos of omega naught plus z power minus 2, which means that x1 of n, which has a z transform of x of z, will be equal to x1 of a inverse z, which is equal to a inverse z whole power minus 1 sine of omega naught upon 1 minus 2 into a inverse z whole power minus 1 cos of omega naught plus a inverse z whole power minus 2, which is equal to az inverse sine omega naught whole divided by 1 minus 2a z inverse cos of omega naught plus a square z power minus 2. The region of convergence here was magnitude of z greater than 1. So here magnitude of z upon a should be greater than 1, which means that magnitude of z should be greater than magnitude of a. Any doubts in this question? Okay. So now we have three questions, three subparts in this question. So first we need to find z transform of unit step function, then z transform of n square into u of n, and then z transform of n into a power n minus 1 u of n. Okay. So let us start with the first one, that is x of n is equal to u of n. Now this can be actually found using the standard definition, that is summation n running from minus infinity to infinity. Instead of doing that, what I'll do, I'll write it as 1 power n u of n. That is, I am writing this in the form of a power n un, and we know that the z transform of this is z upon z minus a, and the region of convergence is magnitude of z greater than magnitude of a. Here my a is equal to 1, then z transform of this is x of z is equal to z upon z minus 1, and region of convergence is magnitude of z greater than magnitude of 1, that is 1. So this is the z transform of unit step function. You will get exact same answer if we go by the definition which was done in the lectures. The next part of this question is x of n is equal to n square into u of n. Now let us go back to the properties of z transform. So if we look at multiplication by n property, this property here, we can see that the z transform of n into x of n is equal to minus z into differentiation of x of z with respect to z. So this I can write as n into x1 of n, where x1 of n is equal to n into u of n. And let's say this x1 of n has z transform x1 of z. So using the property, that is using this property, n into x of n will have a z transform of minus z d dz of x of z. The z transform of x1 of n is simply x1 of z is equal to minus z into d dz of z transform of this unit step function, which is given here, z upon z minus 1. So this we can obtain as minus z multiplied by z minus 1 minus z upon z minus 1 square. This gets cancelled. So this is simply z upon z minus 1 whole square. And again we observe that the region of convergence remains magnitude of z greater than 1. There is additional pole occurring at this location, but it's okay. Now we have found this x1 of z, but we need to find the z transform of n into x1 of n. That is, basically my x of z is the z transform of n into x1 of n, that is, it will be minus z times d dz of x1 of z, that is equal to minus z into d dz of z upon z minus 1 whole square. So this is equal to minus z into z minus 1 square minus z into 2 into z minus 1 upon z minus 1 whole power 4. This we can simplify as minus z inside the bracket z square minus 2z plus 1 minus 2z square plus 2z whole divided by z minus 1 to the power 4. These terms get cancelled and this is equal to minus z into minus z square plus 1 upon z minus 1 to the power 4, which is equal to z into z minus 1 into z plus 1 upon z minus 1 to the power 4, which is equal to z into z plus 1 whole divided by z minus 1 to the power 4. Again here the region of convergence remains same. Sorry, this is z minus 1 power 3. Again here the region of convergence remains same, that is magnitude of z greater than 1. Let us look at the third question. So it says that x of n is equal to n into a power n minus 1 into u of n. Now let us rearrange this something like this, that is n into a inverse into a power n into u of n, which I can write as n by a, or let us write it as, we have this constant 1 by a multiplied by n into a power n u of n. Now this is the standard form that we know. So the z transform of this standard form is simply z upon z minus a, where magnitude of z is greater than magnitude of a. Now if we consider the z transform of this, let's say z transform of this is x1 of z, then this is equal to, using this property of multiplication with time, that is multiplication by n, this is simply minus z into d dz of x1 of z, that is this factor, that is z upon z minus a. So this is equal to minus z minus a minus z upon z minus a whole square. This gets cancelled. This is equal to az upon z minus a square, which implies that the z transform x of z is equal to 1 by a multiplied by x1 of z, that is az upon z minus a whole square, which is equal to z upon z minus a whole square, and the region of convergence remains unchanged, that is magnitude of z is greater than magnitude of a. Any doubts in this question? Okay. If not, then let us look at the next question. And here we need to find the inverse Z transform of this given x of z, that is Z transform. We need to find what is x of n if x of z is this, and we are given three different conditions for region of convergence. So for these three different conditions, we need to find what is the value of x of n. And let us use partial fractions method for this. So for partial fractions method, what we do is we represent x of z upon z as some linear combination of some poles. So before doing that, let us look at this denominator here. So this denominator, which is z square minus 3z plus 2, this can be factorized as z minus 2 into z minus 1. So this can be written as 3z square plus 2z plus 1 divided by z multiplied by z minus 2 multiplied by z minus 1, and this is written as c1 upon z plus c2 upon z minus 2 plus c3 upon z minus 3. Now this we can write as 3z square plus 2z plus 1 is equal to c1 into, sorry, this is z minus 1, c1 into z minus 2 into z minus 1 plus c2z into z minus 1 plus c3z into z minus 2. So let us substitute z equal to 0. Then it implies that the RHS reduces to 1, which is equal to c1 into 0 minus 2, that is minus 2, 0 minus 1, that is minus 1. So this is equal to 2c1, which implies that my c1 is simply 1 by 2. Now let us substitute z equal to minus 1, which implies that 3 into minus 1 power 1, minus 1 to the power 2, it comes out to be 3, minus 2 plus 1 is equal to c3 into minus 1 into minus 1 minus 2. So this is equal to 3c3. Yeah. And this is 3 plus 1, 4 minus 2, that is 2. So we have 3c3 is equal to, I'm sorry, my z is equal to 1. Yeah, I need to cancel out this factor here. I make all the terms that are considering this z, that are having the z minus 1 to 0. So I have, let's say, z equal to 1. Then in that case, this is 3 plus 2 plus 1. LHS is simply 3 plus 2 plus 1. Then this term, first term goes to 0. The second term also goes to 0. And the third term is simply c3 into 1 into 1 minus 2. So this comes out to be minus c3, which means that my c3 is equal to minus 6. Similarly, if I need to cancel out the terms containing z minus 2, I need to substitute z equal to 2, which implies that here I have 3 into 4, that is 12, plus 2 into 2, 4, plus 1 is equal to, the first term goes to 0, the second term remains, c2 into 2 into 2 minus 1, and the third term goes to 0. So this is equal to 2c2, which implies that my c2 is equal to 17 by 2. So I can write this x of z upon z is equal to C1 upon Z, that is 1 by 2Z, plus C2 upon Z minus 2, that is 17 by 2 into Z minus 2, and C3 upon Z minus 1, that is equal to minus 6 upon Z minus 1. Therefore, the Z transform X of Z using partial fractions can be reduced as 1 by 2 plus 17 by 2 into Z upon Z minus 2 minus 6 into Z upon Z minus 1. So this is the X of Z that we have obtained. So what do we have? X of Z is equal to 1 by 2 plus 17 by 2 into Z upon Z minus 2 minus 6 into Z upon Z minus 1. And we need to find this Z transform for different ROCs. So let us look at the first region of convergence. So we have magnitude of Z less than 1. So the first case that we have been given is ROC where magnitude of Z is less than 1. So let us try to draw this first. So if we observe here, we are having two poles. One is at 1 and one is at 2. So let's say the first circle which I had drawn is corresponding to the radius of 1. And the second one is of the radius of 2. And the region of convergence that we are given is this. It is interior to the innermost pole, and this can be obtained when the component corresponding to 2 is also giving an ROC which is interior. That is, for this case magnitude of Z is less than 2. Also magnitude of Z is less than 1. So this one will correspond to the case when magnitude of Z is less than 1, and this one will lead to the case when magnitude of Z is less than 2. And this 1 by 2 is a constant. This will only correspond to one unit impulse. It was seen in the lectures that unit impulse delta n has Z transform as 1, and region of convergence is all the entire Z plane. So this 1 by 2 will just contribute to a unit impulse scaled by a factor of 1 by 2. So this x of n will be equal to 1 by 2 into delta n plus 17 by 2. Now this is Z upon Z minus 2 with magnitude of Z less than 2. So if we observe the standard form here, this one, so it is of this form: Z upon Z minus A, Z upon Z minus 2 with magnitude of Z less than 2. So for that case, my Z transform will be minus 2 power n u of minus n minus 1. So this is simply, we'll have a minus sign here, minus of 2 power n into u of minus n minus 1. Similarly, this factor will be corresponding to 1 power n, so which will be equal to 1 into u of minus n minus 1. Any questions at this point? The second part of the question, or the region of convergence that is been given, is magnitude of Z is greater than 2. So here we have magnitude of Z greater than 2. So again, if we draw it, so now the region of convergence here is everything that is greater than 2. So this region we will get only when magnitude of z is greater than 2 as well as magnitude of z is greater than 1, which means that this factor z upon z minus 2 will be basically z upon z minus 2 with magnitude of z greater than 2, and this will be z upon z minus 1 with magnitude of z greater than 1. That is, if we look at these standard forms, so it corresponds to the first standard form, that is a power n un, which has the z transform as z upon z minus a magnitude of z greater than a. So if we use the same thing, then this x of n will be equal to 1 by 2 into delta n plus 17 by 2 into 2 power n u of n minus 6 into 1 power n, which is 1, into u of n. And the third question, or the third region of convergence that we are given in the question is ROC such that my magnitude of z lies between 1 and 2. That is, it is of this form. So this is 1 and this is 2, and it is entire region which is in this ring between the circles of radius 1 and 2. So it's something like this, and this region is obtained when my magnitude of z is greater than 1 and my magnitude of z is less than 2. So if we consider this z upon z minus 2, it corresponds to this factor. So this term, the second term, will be similar to this part here, and the first term, the third term will be equal to the part which we have obtained here, that is in the second part. So basically my x of n will be equal to 1 by 2 delta n minus 17 by 2 2 power n u of minus n minus 1 minus 6 times u of n. Any doubts in this question? Okay. If not, let us get to the next question. And here what we are asked is, we need to find h of n, where h of z is given as 1 upon 1 minus 1.5 z inverse plus 0.5 z power minus 2. So let us write this h of z, and this we need to find using partial fraction method. So this we can write as z square upon z square minus 1.5 z plus 0.5. This is equal to z square upon z minus 1 into z minus 0.5, which means that my h of z upon z, let me write it in the new line. So my h of z upon z is equal to z upon z minus 1 into z minus 0.5. So this I can write as c1 upon z minus 1 plus c2 upon z minus 0.5, which implies z equal to c1 into z minus 0.5 plus c2 into z minus 1. Now, in order to find c1, let us substitute z equal to 1. If I do that, then my RHS remains 1, which is equal to c1 into 1 minus 0.5, which is equal to 0.5 c1, which comes out to be c1 equal to 2. Similarly, in order to find c2, let us substitute z equal to 0.5, which implies that 0.5 is equal to c2 into 0.5 minus 1, which is equal to minus of 0.5 c2, which implies that c2 is equal to minus 1. Therefore, my h of z upon z is equal to c1 upon z minus 1, that is 2 upon z minus 1, minus 1 upon z minus 0.5, which is equal to 2 into z upon z minus 1 minus z upon z minus 0.5. Now what we have been given is the system is causal. Now for causal system, the region of convergence is always exterior to the outermost pole. So one pole is at 0.5 and other pole is at 1. So for the system to be causal, my region of convergence should be something like this. And this is possible, this region of convergence, which is magnitude of z greater than 1, is possible only when magnitude of z is greater than 1 as well as magnitude of z is greater than 0.5. And if that is the case, then this factor will contribute to the fact that this is 1 power n into un, and this factor will contribute to the fact that this is equal to 0.5 power n into un, and therefore the system impulse response h of n is equal to u of n minus 0.5 power n into u of n. Any doubts in this question?
Madam, the 2, oh,
Yeah, sorry, 2.
2 is
Yeah,
missing.
thank you. Yeah, 2 into u of n minus 0.5 power n un. Yeah, thank you. Any other questions in this? Any other doubts in this question? If not, then let us try to find h of n using power series method, and again we have the condition that it is causal. So in power series method, we divide this one by this denominator polynomial, something like this. So we have 1 here and 1 minus 1.5 z inverse plus 0.5 z power minus 2. So for dividing this with 1, we need to cancel out this 1. So we'll simply multiply this polynomial with 1. So we'll have here 1 minus 1.5 z inverse plus 0.5 z to the power minus 2. And if I subtract this, then this is equal to 1.5 z inverse minus 0.5 z power minus 2. Now we need to subtract or this first factor, so we'll multiply this divisor by 1.5 z inverse. So this is equal to 1.5 z inverse minus 2.25 z to the power minus 2 plus 0.75 into z to the power minus 3. This gets cancelled. This reduces to 1.75 z power minus 2 minus 0.75 z to the power minus 3. Now in order to cancel this out, we will multiply it by 1.75 z power minus 2. So we have 1.75 z to the power minus 2 plus, sorry, this is minus 2.625 z to the power minus 3 plus 0.875 z to the power minus 4, and we'll again go on repeating this process. So this will also continue for all the values of z. So this h of z we can write as 1 plus 1.5 z inverse plus 1.75 z to the power minus 2 and so on. Now this z inverse, this z to the power minus 1 implies that this is a unit delay. And from where does this concept come? So for that, let us look at the time shift property. So if we observe here, if we look at this, this time shift property here, so if my n naught is equal to 1, if my n naught is equal to 1, then in that case we have x of n minus 1, that is we have a delay of 1 unit into z power minus 1 x of z. So this z power minus 1 simply implies that it is nothing but a unit delay. That is, if I have a constant which is multiplied by z power minus k, then this a has a this a has an inverse z transform of a into del of n, and this together will have a z transform using the time shift property as a into del of n minus k. So this 1 will be del of n, this will be 1.5 into del of n minus 1 plus 1.75 delta n minus 2 and so on. And this can be represented using a, so this is h of n, this can be represented using a sequence something like this, which is 1, 1.5, 1.75 and so on. And to indicate that this 1 is located at 0, we just put an up arrow below this 1. Any doubts in this question? So basically we just found h of n of the same transfer function using two ways. One using partial fractions method and other using power series method. Yeah, any questions?
But where did we use the causal property, madam? Here?
Yeah, the causal property is used actually here. Actually, if you observe, this is unit delay, right? This is actually, if I'm having z power minus 1, this is shifting the entire thing rightwards by 1 unit.
Okay.
So if we are multiplying it by z power minus 1 plus 1 plus 1.75 z power minus 2. So this z power minus 1 is just shifting my unit impulse towards right hand side. So this is
Okay. Right.
making it causal. Now suppose we need to have an anti-causal system. Then for that I'll represent this as z square upon z square minus 1.5 z plus 0.5, and when I'm dividing it, what I'll do is it will be in multiples of z, z square, z cube, and so on.
Yes.
Yeah, so if I do this, then it will be an anti-causal system or non-causal system. But if I have the division terms which are coming like z power minus 1 and so on, then it will be a causal system.
Okay.
Yeah,
So here that any method we can use, is it power series or partial fraction? If it is not,
any method we can use. Both will give you same answer. The only thing is if I am having a simple thing which is easy to factorize and other stuff, and then it is easy to go with this format because it is giving me a closed form. Here I am not getting a closed form, I am just getting a sequence. So if it is possible that your transfer function is very simple, then you can simply go with your partial
okay.
fractions method.
Okay, how can here it is giving a closed form, there it is giving a series. A series must be converged, it should be fine. Oh, oh, that is surprising. That
Here we are not looking at convergence of series.
okay.
It's
The
simply a representation of it. Like this will give you the same series that we are having here. Now it's not possible every time to look at the series and come up with this form.
okay, okay,
Or we
okay.
can do this. We can write it as 2 minus 1, 2 minus
Yes.
zero point 0.5, 2 minus 0.25, and so on. So this is
Okay.
simply 2 minus zero point 0.5 to the power 0. This is 2 minus zero point 0.5 power 1. And this is 2 minus zero point 0.5 square. So in together I can simply write it as 2 into, this is not visible here. Yeah, I can simply write it as 2 into u of n, since my n is starting from 0, that's why 2 into u of n minus 0 0.5 power n into u of n. It's same thing.
Okay. 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 But the that x of n is different in these two
No,
examples. What we got in inverse, it's different, right?
no.
In the earlier one with the power with partial fractions, x of n, oh, it is the same thing. We substitute n is equal to 0. Yeah, if we substitute n is equal to 0, it's the same thing.
Yes, it's the same thing. If I have
Here,
n equal to 0, then it is 2 minus 1.
oh, okay, okay, right,
Yeah.
right, okay. Yeah, thank you.
Okay, if there are no further questions, let us.
You are, sorry,
Yeah.
sorry, sir.
Okay, if there are no further questions, let us look at the next question. So here I have been given an input-output relation of an LTI system where y of n is equal to 3y of n minus 1 plus 4y of n minus 2 plus xn plus 2 times x of n minus 1. Now we need to find the impulse response h of n. Now instead of substituting the value of n and other things, and let's say that the initial conditions are 0, so we can just simply use the Z transform. That is, we can use the Z transform for LTI systems. We can use this form. We can find y of z, which is equal to x of z into h of z, and then simply find h of z as y of z upon x of z. So here what we have is, let's say my input x of n has z transform x of z, and my output y of n has z transform y of z, and my h of z into x of z is equal to y of z. So now let us try to find the z transform of the given transfer function. So what do we have is, y of n is equal to 3 times y of n minus 1 plus 4 times y of n minus 2 plus x of n plus 2 times x of n minus 1. So let's say my y of z, that is, I am taking z transform. So this y of z is 3 times, this is time shift property, that is y of n minus n naught will have a z transform of z power n naught into y of z. So this will be 3 into z inverse y of z plus 4 into z to the power minus 2 y of z. The z transform of x of n is, let's say, x of z plus 2 times z inverse x of z, again using the time shift property for x of n. So I'll take all the terms corresponding to y of z to one side. So we have y of z, the bracket 1 minus 3z inverse plus 4z to the power minus 2. This is equal to x of z common multiplied by 1 plus 2z inverse. Therefore, y of z upon x of z is equal to h of z is equal to 1 plus 2z inverse whole divided by 1 minus 3z inverse plus 4 to the power minus 2, 4z to the power minus 2. This I can write as z plus 2 upon z upon z square minus 3z plus 4 upon z square. So 1z comes here. So these two are equivalent expressions, and now we need to find h of n, impulse response, and we are assuming that we have a causal system here. So this we are taking as an assumption. So let's say this h of z is given by this formula, and this I can further simplify as z into z plus 2. Sorry, this is minus sign. Upon, so this is z upon z plus 2 upon z minus 4 into z plus 1. So let us use the partial fractions method to find the impulse response. So for that we have h of z upon z is equal to z plus 2 whole divided by z minus 4 into z plus 1 is equal to c1 upon z minus 4 plus c2 upon z plus 1, which implies that z plus 2 is equal to c1 into z plus 1 plus c2 into z minus 4. So for that, for finding c1, let us substitute z equal to 4. So if I have z equal to 4, then my right hand side becomes 4 plus 2, that is 6. which is equal to C1 into 5 C1 into 5, and this term goes to 0. So this implies that my C1 is equal to 6 by 5. Similarly, if I need to find C2, I substitute Z equal to minus 1, so that I can cancel out this factor here. So here I have minus 1 plus 2, that is 1, which is equal to Z C1 into Z plus 1, so this gets cancelled out due to Z equal to minus 1, and here I have C2 into minus 1 minus 4 minus 5, which implies that C2 is equal to minus 1 by 5. So this implies that I have h of Z upon Z is equal to C1 upon Z minus 4, that is 6 by 5 upon Z minus 4. So this is 6 by 5 into 1 upon Z minus 4 minus 1 by 5 into Z plus 1, which implies that h of Z is equal to 6 by 5 Z upon Z minus 4 minus 1 by 5 Z upon Z plus 1. Now this is having a pole at 4 and this is having a pole at minus 1, and the condition that we are given is we have region of convergence outside the outermost pole, that is, this is the radius of 1 and this is the radius of 4. Then for the system to be causal, my region of convergence will be something like this. We have a pole at minus 1 and a pole at 4. For this term, the region of convergence will be magnitude of Z. For this term, my magnitude of Z will be greater than 1. And for this, my magnitude of Z should be greater than 4 for the system to be causal. So in that case, using the standard definitions, h of n will be equal to 6 by 5. Here the value of a is 4, so it will be 4 power n u of n minus 1 by 5. Here the value of a is minus 1, so it will be minus 1 to the power n u of n. So this is the impulse response that we have. Any questions at this point? Okay. If not, then let us look at the next question. So the question says that we need to find which of the following systems are causal and or stable or none. So we need to find whether the given system is causal or it is stable, or it is neither causal nor stable, or it is causal but not stable, or stable but not causal. So basically we need to comment on the stability and causality of the systems whose transfer function are given to us. So let us try to see these questions. So the first one that we have been given, the very first one that we are given is h of z is equal to 1 minus z square minus 5z to the power minus 7. And the ROC is given as z not equal to 0, which means that it is entire z plane, but only 0 is not included, which means that this condition, that is magnitude of z is equal to 1, is included, which means that region of convergence includes the unit circle. So this magnitude of z equal to 1 is simply my unit circle. And if my unit circle is included in region of convergence, just a minute. If you have some issues with my internet, please let me know. Yeah, okay. So if yeah, yeah. So this unit circle is included in ROC. So since unit circle is included in my region of convergence, this system is stable. Yeah. Now let us look at this. We'll just try to find what is h of n. So this h of n is basically this one. This one has inverse Z transform as delta n minus, using the time shift property with n not equal to minus 2, this has inverse Z transform as Z plus 2 minus 5 times Z of n minus 7. So if we draw this, it is something like this. So this is 0, this is minus 2, and this is 7. So at n equal to 0, I have 1, and at n equal to minus 2, I have minus 1, and at n equal to minus 7, I have minus 5. So if we look at this part, that is at n equal to 2, at n equal to minus 2, h of n is not equal to 0, which means that this system is non-causal. Are there any questions in this?
Madam, now without getting into the impulse response, by looking at H of Z, can't we make a statement about stability and causality? Because stability we already made a statement. Similarly, causality we can't make a statement.
No, we can't make a statement by just looking at region of convergence. By looking at h of z, we can say. But what will you say about this third question? Can you just look at this and tell if it is stable or not, or if it is causal or not? Let's not say about any stability. Stability we can get about from ROC.
Okay, okay.
Yeah. So if I have a simple transfer function which is something like this, from this we can easily say that it is non-causal. So if I have a positive exponent here, when my denominator polynomial is just 1, then in that case, if I just look at the power of z, then I can clearly say that if any of the power is non-positive, or if it is less than, or if it is greater than 0, then definitely it is a non-causal system if my
Oh,
transfer
okay,
function is
okay,
like this.
okay, 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 okay. So the idea is in Z transform, if any power of Z is positive, then by default you can make a saying that it is non-causal. Okay, okay.
If the Z transform is of this form, that is, if my Z transform is H of A equal to summation I AI Z power minus I.
Okay, some polynomial,
Yes, some
polynomial.
polynomial, and
Oh,
there shouldn't be anything in denominator.
okay, any polynomial which contains Z of positive exponent,
Yes,
then we can say it is non-causal.
yes.
Okay,
Why?
okay, okay.
Because that positive power will shift your signal, your unit impulse, leftwards, which is happening
Left.
here.
Yes, yes. So anyone, right? Need not be all
Anyone,
exponents.
anyone.
Okay,
Even
okay,
if you have anything, if you have h of n not equal to 0, even at n equal to minus 100, it is a non-causal system. For any value of n which is negative, if I have a non-zero impulse response value, then it is non-causal system.
okay.
Yeah. Okay. Okay, so now let us look at the next part of this question. So here h of z is equal to z upon z minus 2, and magnitude of z is greater than 2, and this is of our standard form, so we can clearly see that this h of n is simply 2 power n into u of n. Now this is non-zero. This u of n makes h of n is equal to 0 for all n less than 0, which means that this system is causal. So this is causal. Now for stability, let us look at its region of convergence. So let's say this is 2, I have a pole here, and my region of convergence is outside this circle, something like this. Yeah. And the unit circle is somewhere here. So we observe that this unit circle is not in my region of convergence, which means that the system is not stable, or the system is unstable. Is this okay? Now let us look at the next part. Here h of z is equal to z cube upon z minus 2, magnitude of z greater than 2. Now the region of convergence is same as that of this. That is, I am having same region of convergence. So for convenience, I'll just draw it again. So this region of convergence is here, which is 2, and it is outside this circle of radius 2. And my unit circle is again not included in my region of convergence. That is, mod of z equal to 1 is not included in ROC. Therefore, it is unstable. What about causality? So for that, we have this z. We can write this h of z as z square into z upon z minus 2, and region of convergence is magnitude of z greater than 2. We know that this part has inverse z transform as 2 power n un, but now we have this factor here, and now we'll again use the time shift property, which we know that if I shift x of n minus by a factor of n naught, then the z transform of this is simply z power minus n naught into x of z. So here my n naught is basically minus 2. So which means that I'll have to shift the n by a factor of 2. So this h of z is equal to 2 to the power n plus 2 into u of n plus 2. So if we
Madam, I got confusing here. It says small h of z and
sorry, h of n equal to, so I'm taking inverse z transform. Is it okay now? So was this your confusion or there is something else?
no, even it's confusing. The above h of z is equal to z square dot z by z minus 2. How could you find the inverse? Uh, Inverse of z by z minus 2, I understand. That is correct. Uh, u of n plus 2. Sorry. Yeah, u of n plus 2. N plus 2, n minus. Okay. Okay.
So you need to you are not understanding how this factor z transform is coming like this.
Yes,
Okay,
yes.
I'll
So,
redo it, no problem. No problem. Okay, let's do it in this way. So I can write this as this. Is this fine till this point? Z
yes,
square
yes.
into z upon z minus 2. So I can write it as z square into h1 of z, let's say. And h1 of z is equal to z upon z minus 2 with region of convergence magnitude of z greater than 2. And we know that inverse z transform of this is, let's say, h1 of n, and this is equal to 2 power n u of n. This much is okay?
Yes,
Okay.
yes.
Now what do we have is z power 2 h1 of z. Now let us see what is my time shift property again. So see, here we have the time shift property. If I shift x of n by a factor n naught, we get a scaling of z to the power minus n naught.
Okay.
So here, let's write it in terms of h1. So my h1 of n has z transform as h1 of z. So if I shift
Yes,
its h1 of n by a factor of n naught, then this will give me z power minus n naught into h1 of z. Okay,
yes.
now compare this and this.
Okay,
So here if I compare equation 1, so here my n naught is equal to minus 2.
okay.
Then if I take inverse z transform of h of z, then h of n will be equal to h1 of n minus n naught, which is equal to h1 of n plus 2. This is equal to 2 to the power, just replace this n by n plus 2 into u to the power n plus u of n plus 2.
Okay. Okay.
Okay, this is clear. Now let us look at this. So we have obtained h of n is equal to 2 to the power n plus 2 into u of n plus 2. So if we sketch this, so let me sketch this. So this is my n axis, this is 0, this is minus 1, minus 2, minus 3, 1, 2, 3, and so on. U of n plus 2 is non-zero, So this is non-zero for all the values of n plus 2 greater than or equal to 0, which means that n greater than or equal to minus 2. So at n equal to minus 2, this 2 to the power n plus 2 will take the value of 2 to the power minus 2 plus 2, so it will be 1. So this will be 1. Then at minus 1, it will take the value as 2, then 4, 8 and so on. And here it will be 0, again at minus 4, 0, 0, etc. Now we can observe here that for minus 2 and minus 1, my h of n,
Madam, that n plus 2 greater than or equal to 0, is that a causality
no,
statement? That, is that given? Or
no, this is your n, see, this is your unit step.
Yes, yes.
Okay, so in general, how my unit step
Oh,
is defined, u of n.
okay. So it's greater than 0 only, it will be 1.
Yes,
Okay, fine. Thank you.
yeah, okay. So at n equal to minus 2 and n equal to minus 1, my h of n is non-zero for n equal to minus 2 and minus 1, which are negative values, which means that this is non-causal. Any questions in this part? So this system is neither stable nor causal. So now in this case, if we look carefully, we are having the z cube upon z minus 1, and the region of convergence for this question, this one, that is part 2 and part 3 was exactly same, but it here the previous h of n, this one was a shifted version and the shift was leftwards, and because of that we had non-zero impulse response at some negative values of n, and hence it is a non-causal system. Let us look at the next question, last part of this question, that is we are having h of z is equal to z upon z minus 1 by 2, and here magnitude of z is greater than 1 by 2. Now again this is our standard form, and we know that h of n is equal to 1 by 2 to the power n u of n. Now let us look at its region of convergence. So we have this circle of 1 by 2 and we have a pole here, and this is my unit circle. This is of radius 1, and the region of convergence is something like this. So we observe that this includes unit circle, which means that it is a causal system. It is a stable system. Now again, this unit step function which is arising here is making this unit step is equal to 0 for all n which is less than 0, which implies that my h of n is equal to 0 for all n which is less than 0, which means that it is a causal system.
So generally, any function multiplied by unit step function u of n makes it causal. Okay. Okay.
Another thing that I forgot to mention from last two parts is in both the parts the region of convergence is exactly same. That is, if it is outside the outermost pole, that is, it is mod of z greater than 2. But this system, this one, This one is causal, but this one is non-causal. So if in case you have been given just the region of convergence and then asked to comment about the causality, we can't do it. Which means that for a causal system, when we looked at the properties, for a causal system, the ROC is always exterior to this outermost pole's radius. But if I have been given an ROC where it is exterior to the outermost circle, I can't say that the system is causal just by looking at its region of convergence. Because you can simply see from these two parts, same region of convergence. But one is causal and the other is non-causal just because of a shift which is causing an addition of 0. So this point has to be clear, that just by looking at the region of convergence you can't comment on the causality. You should know where the poles and zeros exactly lie, how the transfer function is, and then only you can comment on its causality.
Madam, generally the zeros, we are not discussing anything about zeros. What is the importance of zeros in our
Okay, the importance of zeros is actually, if you observe carefully, these zeros bring down the magnitude of this h of z to 0.
Okay,
So this
okay,
is actually, this zeros and poles make a significant difference while designing filters.
okay,
So if you have a filter where you need to uh, what we say, you need to so we have high pass filter, low pass filters, right? That is, we need to reject some frequencies and we need to keep some frequencies. So if I need to reject some frequency, then I'll set my zero in such a way that its transfer function goes to 0 at that frequency.
okay, okay. But otherwise, for causality and stability, we need not look at zeros, only poles
For
and everything.
causality we need to look at zeros.
For stability also, only poles only, right?
For
Units.
stability we just need to see if the unit circle is included.
Okay, okay. Yes,
Yeah.
yes. Okay.
Okay, so let us look at the last and a very simple question. So this is actually complex conjugate property of Z transform. That is, suppose x of n has Z transform as x of z, then what is the Z transform of x conjugate of n? So let's say it is x1 of z, and this asterisk sign basically implies complex conjugate. Okay. So let's start with the definition. So we have x1 of z is equal to summation n running from minus infinity to infinity, x1 of n, which is x conjugate of n, z power minus n. So let us take complex conjugate on both the sides. So x1 conjugate of z is equal to summation n running from minus infinity to infinity, x of n, z conjugate of minus n. So this is equal to, if you observe it carefully, this is simply equal to x of z conjugate, which means that x1 of z conjugate, x1 conjugate of z is equal to x of z conjugate, which means that x1 of z is equal to x conjugate of z conjugate. Therefore, the z transform of this function is simply x conjugate of z conjugate. And now the region of convergence should be such that this z conjugate belongs to the region of convergence of this z1. So suppose this has a region of convergence r1, then z conjugate should belong to r. So this is also an important property, or maybe it's sometimes useful when you are dealing with complex signals. which is very rare case, but still.
Okay, madam, in the second equation, x1 conjugate of z, when you're taking conjugate both sides, the the conjugate of conjugate is same, right? Xn.
Yes.
So that's why you are not to put xn. Okay. In the second equation, the conjugate is missing because conjugate of conjugate is the same.
Yes, it's like this. If I have a complex number a plus jb, just its conjugate is equal to a minus jb. If I again
Okay.
take the conjugate,
Okay.
it will be equal to a
Okay.
plus jb.
Okay. 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 Sorry, madam. I am a senior citizen. I am doing it after long 30 years of undergraduation in complex
No, no,
variables.
it's
Okay.
fine.
Okay. And another question, madam. So in the similar one, if x of z is a z transform of x of n, x of minus z, what would be the inverse?
You need to find x of minus z.
Mi- yeah, minus z.
So you have x of minus z you are having, right?
Yes. Then x of minus z,
So let me try
what would
it
be the
once.
yeah.
If it makes some sense. X of n is equal to 1 minute. So what you are saying is x of z is equal to summation n running from minus infinity to infinity x of n z power minus n, and you want x of minus z, so this will be equal to summation n running from minus infinity to infinity x of n. I'll just replace it by minus z to the power n, so this I can minus n, yeah, sorry. Summation n running from minus infinity to infinity minus 1 to the power minus n into x of n into z to the power minus n. So basically this is z transform of minus 1 to the power minus n into x of n. This is my x1 of n. So,
Yes.
so if I have minus 1 to the power n x of n, then its z transform is simply x of minus z.
Okay.
Yeah.
Okay. Thank you, ma'am.
So this was all that I had planned to cover today. If you have any sort of doubt, please let me know.
Okay. Thank you, madam.
Thank you.
Thank you. Madam, generally in the examination, do you have to remember all the properties of Z transforms, Laplace transforms? Because there's a big table, and so assignments is okay because we refer the table and do it. But in examination, I don't know. We have to remember means we have to learn by heart, right? All that, some of these
Even
things.
if you don't remember the properties, you can go with the basic definition, and
Okay.
at that time just try to derive those properties. You just look at the derivations once. It's very simple.
Okay. Okay.
So once you know the
Okay.
derivation, you will automatically have some intuition that okay, like if I'm having x of minus n, and if I look at this factor here, I'm having x
Okay.
of minus n, then to make it x of n, I'll just replace minus n by n. So that is going to
Okay.
just affect my this factor.
Okay.
So like
Okay.
that you will be able to build the intuitions.
Okay. And another, suggestion is, see, for example, there is a Laplace transforms, there is Z transforms, and there is a Fourier transforms.
Yes.
Okay. So there is a relationship between all these things. Is there any place, one cheat sheet kind of thing, one big sheet where all related things put together? so that it's easy for no recap just before exam, or that comparison, because all are related, right?
Yes.
So all, that one is derived from the other.
Yes.
Uh,
If I find
so
some, I'll post
yeah,
its
yeah.
link in next lecture.
Yes, yes, madam. That will be very useful because that I'll keep it pasted in my notebook. So at least before exam. So the interrelationship is what actually is interesting. We can see.
Yes.
Okay. Fourier transform and Laplace transform and Z
Yes.
transform. Yes. Okay. Okay, madam. Thank you.
Thank you.